Hello everyone, this is Arjun Bhadwaj. Today I'll teach you about the QUIC. This is the demonstration video of SD task of SIT 202 Networking and Communications. So let's start. So first of all, I'll tell you about the evolution of the HTTP model. Why we need new HTTP model, that is QUIC. So first of all, there is a new model. There is old model that was HTTP 0.9, which was called the one line protocol. So in this protocol, it was the initial version of HTTP circa 1991. Then it was extremely simple request, consisted of a single line, and it was only possible to use get method, transmits HTML files. Then after in 1996 we have HTTP 1.0 version, which was called building extensibility. In this version, information sent within each request, HTTP 1.0, was appended to the get line. Addition of status code line included at the beginning of a response, allowing browser to recognize success or failure of a request. Concept of HTTP headers introduced for both requests and responses. Metadata can be transmitted, making the protocol more flexible. Addition of content type headers. Document other than plain HTML files can now be transmitted. Then in 1997 we have HTTP 1.1, which is called the standardized protocol. In this protocol, persistent HTTP introduced, meaning a connection could be reused. Pipeline was added. Chunked responses were also supported. Content negotiation, including language encoding and type, was introduced. And there was an introduction of the host header, allowed server collocation, different domains from the same IP address. Then we have the HTTP 2, which is a protocol for greater performance. In this protocol, it used binary rather than a text-based protocol, allowing for improved optimization. In this protocol, there was multiplexed protocol. Parallel requests can be made over the same connection. It compresses headers, removing some duplications and overhead of data transmitted. There was a server push, allows a server to populate data in a client cache. Now, the question is why we need HTTP 3 model. So in this, there were some problems with the HTTP 2, which were connection time establishment, TCP head of line blocking, server load spikes, and because of these problems, we need updated version of HTTP, which was HTTP 3. So now we have the question: now what is QUIC? What is it? So the QUIC or QUIC UDP internet connections emerges as a transformative internet protocol developed by none other than Google. So to enhance it was developed by Google to enhance the speed, security, and efficiency of online communication. So now, what is QUIC? QUIC is defined by the Internet Engineering Task Force, represents an encrypted connection-oriented protocol operating at the transport layer 4 of the OSI model. Initially developed by Google engineers in 2012, QUIC aims to streamline web applications performance by leveraging UDP. Yes, you heard right, it works over UDP instead of TCP, thereby reducing latency and improving speed. Now, what is the motivation behind QUIC? I'll discuss this. So the primary motivation behind QUIC's development is speed. Unlike traditional protocols like HTTPS over TCP, QUIC accelerates data transmission by minimizing the time required for connection establishment. By initiating encryption and key exchange in the initial handshake process, QUIC significantly reduces round trip time. You can see in this GIF how the difference between HTTPS over TCP plus TLS and HTTPS over QUIC. You can clearly see the difference between round trip time in this GIF. So QUIC significantly reduces round trip time, which offers a faster and more responsive user experience. Now I'll discuss the functionalities and frame formats of the QUIC model. So key functionalities of QUIC includes packet exchange mechanism to reduce data loss, integrated congestion control mechanisms for efficient network utilization, utilization of UDP transport to bypass TCP head of line blocking, high security standards, similarly like TLS, ensuring data confidentiality and integrity. It also includes error connection mechanisms and retransmission strategies to enhance data integrity. Now I'll tell you about the advantages and disadvantages of a QUIC model. So advantages include substantial reduction in round trip. I already discussed with you guys. Leading to faster content delivery, enhanced security through robust encryption and authentication mechanisms, improved multiplexing capabilities, minimizing the impact of packet loss on overall performance. So there are some advantages, or we can say challenges, of QUIC model. This includes challenges in traffic visibility and application control for network administrators, potential compatibility issues and deployment complexities when integrating with QUIC into existing infrastructure. So now I'll tell you about network application leveraging QUIC. So you can see in this graph, this is the graph of the websites which are using the QUIC model. So major players like Google and Facebook have embraced QUIC for its speed and efficiency. With over 42% of Google's traffic and 75% of Facebook traffic now utilizing QUIC, the protocol has become increasingly prevalent in the online ecosystem. You can see in the graph also. Now here a question arises: why have these companies all in to use this model? So it goes beyond just the benefits we have discussed so far on initial latency. There is also a benefit of multiplexing. While the HTTP2 protocol does allow multiple HTTP streams to share a single TCP connection, there is still a problem with packet loss. Since TCP is a connection-oriented protocol and needs to recover the lost data, any packet loss on any of the multiplexed streams would lead to all streams on that connection becoming blocked until that loss is recovered. It's like being on a highway and one person tapping the brakes on a single lane and all lanes come to a halt. So here QUIC resolves this issue by enabling each lane to keep running independently. UDP indifferent to the lost packets, the protocol has defined the retransmission parameters and enables the retransmission of data in just one stream. You can see in the diagram also here the different lanes, and whereas in HTTP2 only a single lane. I'm just understanding you guys with an example only. So there is no slowing down in other lanes in the case of QUIC model. But in the QUIC model, there are some security implications. While QUIC offers enhanced security features, its proprietary encryption poses challenges for network visibility and traffic analysis. I already discussed this in the disadvantages of QUIC also. Network administrators may face difficulties in identifying and controlling applications using QUIC, necessitating alternative approaches for network management. So network management considerations include the rise of QUIC. QUIC presents both opportunities and challenges for network management. While QUIC optimizes network performance and bandwidth utilization, it also introduces complexities in traffic analysis and security enforcement. Network administrators must adapt their strategies to effectively manage QUIC traffic while ensuring network security and compliance. Now I'll discuss about by showing you the live example by using Wireshark. So here we have, I am capturing the Wireshark by filtering the QUIC mode. So first of all, we have already talked in the past how QUIC is built over UDP. You can see here UDP, user datagram protocol, over UDP, and we saw why that was not. Now it can be integrated into almost any kernel in the entire world, right? They all support UDP, so QUIC can use that to gain entry into a device and into the kernel. So first, some interesting things that you are going to notice. So QUIC first sends this initial packet. This is the initial packet, you can see here. There are three handshake: first initial, and then the protected encrypted layer here. So in the initial packet, this is the larger packet length, so that's different than TCP, right? Because in the TCP handshake, those are really small packets. You only see 72 bytes, 74 bytes for the SYNAC, depending on the options. But here QUIC comes right out of the gate with the larger packet. So some of the parameters, so for example, max data, max stream, data bidirectional. This shows us initial source connection ID. Alright, so we are advertising that to the other side, max UDP payload size. So 14.72, that's the max that we can put inside a UDP payload. So there are several parameters that are communicated to the other side, and in a way we could again think of those almost like TCP options. So it's just showing how many streams, what's the limit per stream that can be sent, and then the limit for the overall data that's coming in. Now something else that we are going to notice down here on the bottom padding. So again, the first initial packet for QUIC is usually very large. In fact, it's usually very close to the maximum frame size, and the padding is what makes that happen. So it's common to see that initial packet also with a padding packet. So there's no real data in there, but technically it's a QUIC pad that goes into that QUIC packet. All right. So one more thing before we leave this packet that would like to take a look at is also the QUIC connection information. Now down here we see the destination connection ID and the source connection ID. Now these connection IDs are really important, and each endpoint selects the connection ID for the opposite side. So you can see this is a long scary looking number, but what this does is it uniquely identifies the QUIC connection. Now that connection can live on even if the underlying protocols change in some way. So let's just say a UDP port changes, or if there's a change in the IP addressing, if anything changes in those four tuples, so the two IP addresses and the two UDP ports, the QUIC connection can still live on. This means that you can start this YouTube video and you can do it over your home Wi-Fi, and you can have QUIC connections providing the video, and as soon as you walk out of your car, you flip over to an ITE network. Well, the underlying network changes, your IP addresses change, the port numbers could change, but the QUIC connections could stay the same, and so it just migrates into that new conversation. It can take a new network path, so that's one of the advantages to QUIC, is it seamlessly can migrate even if the underlying protocols change, and that's all due to this connection identifier. This identifies the connection on those two endpoints. So here we can see we are using a pretty large number of for the other side. Here you can see is crypto and padding. So in QUIC, crypto refers to the cryptographic handshake and encrypting mechanisms used to establish secure communication channels between the client and server. During the handshake phase, QUIC negotiates encryption parameters, exchanges cryptographic keys, and establishes shared secrets to protect the integrity and confidentiality of data transmission. QUIC employs modern cryptographic algorithms such as AES Advanced Encryption Standard and CHA-20 with the cryptographic along with cryptographic primitives like HMAC hash based message authentication code to ensure robust security. The crypto layer in QUIC handles key exchange, encryption, decryption, and authentication processes, providing end-to-end security for quick connections. Now I'll tell you about the padding. What is padding here? In network protocols like QUIC, padding refers to the insertion of additional data, usually random or meaningless bytes, into packets to adjust their size or shape. Padding is often used to meet minimum packet size requirements, align packet boundaries, or obscure the true length of transmitted data to enhance security. In QUIC, padding may be applied for various reasons, including packet size, optimization, mitigation of traffic analysis attacks, or adherence to network protocol specifications. While padding increases the size of packets and may introduce additional overhead, it can also enhance security by making it more difficult for adversaries to infer information about the transmitted data based on packet sizes or patterns. However, excessive padding can impact network efficiency and performance, so it is typically used judiciously in QUIC implementation. So, in conclusion, I would like to end this video. In conclusion, QUIC stands at the forefront of internet protocol innovation, offering unprecedented speed, security, and efficiency for online communication. As QUIC continues to gain traction across the digital landscape, network administrators must stay abreast of its implications and adapt their management strategies accordingly to optimize network performance and security. Thank you so much. This is from my side. Thank you.